This is the lecture for the Chapter 13 notes, Electrons and Atoms. We begin class usually before I start the PowerPoint with a discussion of how your location on the planet Earth will give you some assumptions about the characteristics of a person. For example, I grew up in the town of Greenfield, Illinois, obviously, and our town was basically a small farm community of nothing but a bunch of white people. So if you made some assumptions about a person coming from Greenfield, you would first assume they are English speaking, and you would assume that they are Caucasian, and you would probably assume that they have something to do with farming. Now in my case, my dad was a teacher, but my mom's parents were farmers, and everybody that lives in the county basically has some agriculture background, so you can make some assumptions just because of their location. And how does that relate to Chapter 13? Well, if you can determine the location of the electrons in an atom, you can determine some of the properties based on just where it's located outside the nucleus. So we start with the atomic models, and there's a figure that I referred to, 13.2, which is in a later slide. So we begin with the first atomic model, which represents the atom, and it was discovered or discussed or invented, I guess is the correct term, by a guy named Thomson. And J.J. Thomson discovered the electron. So in his model, there was a ball of positive charge that contained a number of electrons, and there isn't any nucleus because it wasn't discovered until later, and it's often described as the plum pudding model, or the plum pudding atom, which is a bad description because since he was from England, people know what plum pudding is, but in America nobody has a clue. And so we usually describe it as the chocolate chip cookie dough model, where the chocolate chips would be the electrons and then the dough would be the positive charge. Then the next model was Rutherford's model, and it was expanded on it was expanded from Thomson's model, and as you see in the diagram on the right side, there is a nucleus and it has a positive charge, and then there were electrons that surrounded this positive nucleus. There were no neutrons yet because they hadn't been discovered, and the electrons were just kind of hovering there. They didn't have any orbits because that was discovered later on as well. So Thomson's model had the positive charge all over the place. Rutherford's model had the positive charge in the nucleus. The third atomic model is Bohr's model of the atom, and that kind of reminds people of the Jimmy Neutron symbol. That's where I got the picture on the right from. And he had a nucleus of positive charge just like Rutherford did, but now he has neutrons in his nucleus, and the nucleus is encircled by electrons that have a definite orbit. So it's sometimes called the planetary model. Now these electrons have fixed energies, which means as long as they stay in the same orbit, they're not going to be spiraling towards the nucleus. So they contain the same number of they contain the same amount of energy as long as they're spinning. And they don't lose any energy unless they were to fall to a lower energy level, and they can't fall. The last model is the quantum mechanical model, which is what we use today. And the quantum mechanical model has no definite shape to the electron path, so instead of the electrons spinning around in nice little circles, it's more of a fuzzy cloud. I describe it as bees circling a beehive. Most of the bees are located near the hive, but there's not a definite distance that they are from the beehive representing the nucleus. Now the orbits of the electrons are based on the probability of finding the electron in a particular orbital shape. So probability is sort of like the odds of finding the electron in a certain location. So it's like if you're gambling, the odds of rolling a 7 on a pair of dice or something like that. And most electrons are found close to the nucleus, and then if you go a little farther away from the nucleus, there wouldn't be any. And then if you travel even further away, you'd again hit a region of high electron density. We'll talk more about probability of finding the electron later on. This is a picture of a Bohr model. You can see it kind of looks like the planets around the sun. And here's another example of the Bohr model that I found from online. You can see hydrogen has 1 electron, helium has 2, lithium has 3, and sodium has 11 electrons. This happens to be sodium-22, which means it has 22 protons and 22 particles in the nucleus, 11 protons, 11 neutrons, and 11 electrons circling the outside. And you can see that not all of the electrons are at the same distance from the nucleus, and we'll discuss that later. The quantum mechanical model is more of a fuzzy cloud of electrons, so it kind of reminds you of bees, again, circling a beehive. Here's another picture of the quantum mechanical model. The fuzzy clouds are a little more distinguishable from each other. You have clouds that are called S clouds, and you have clouds that are called P clouds, and we'll discuss those shapes later. And here's a summary of all the models. We didn't talk about Dalton's model, but his model basically is a solid ball where the atom doesn't really have any parts. Thomson's model has the protons or the positive charge and the negative charges just kind of like hovering around each other. Rutherford has the nucleus. Bohr has the orbits, sort of like the planets, and the electron cloud model, or the quantum mechanical model is more of a fuzzy cloud. Now the next slide has the definition of energy levels. Energy levels in an atom are sort of like the rungs of a ladder, and the more energy that an electron has, the farther away from the nucleus it's going to be. So as you move up the ladder, you move away from the nucleus, and they're going to have higher and higher energies. The energy levels, as you see on the diagram, are not evenly spaced. They actually get closer together as you travel farther away. So the difference between energy level 1 and 2 is rather large, but the distance between energy level 4 and 5 is a lot closer. If you want to move from one rung of the ladder to another, you need to be hit with a certain quantity of energy called a quantum. A quantum is a specific amount of energy to jump from one level to another. It's not like an electron can store up energy, and then when it gets enough, it can move. It has to be hit with exactly the right amount before it can jump up. Here's a picture of what a quantized energy level would look like. If you're going to be hit with a quantum of energy, it would be like going up a staircase where you have to have a certain height to get to the next level. A ramp would be a continuous amount of energy, and we now know that atoms do not have a ramp description of energy levels. It's a quantized energy level where each distance is a certain amount of energy, a very specific amount. Now what's different about this staircase from the last picture is that the stairs are evenly spaced, but we know that as you get into an atom's energy levels, they get closer together as you get farther and farther away. Now we have another definition called quantum numbers. A quantum number is basically describing the location of the electrons in a nucleus, and the quantum numbers are sort of like the address for where the electron lives. And this information is going to be used to determine three things. Number one, the chemical and physical properties of the elements. Number two, it also can tell you how the periodic table is organized, why it kind of looks like it's in sections or big gigantic blocks. That relates to the electron address. And it also shows how and why the elements combine the way they do to form compounds. So if you've ever wanted to know why water is H2O and not H3O or H4O5, and why hydrogen can bond with oxygen and stuff like that, it comes from the electron address. Now I describe the four quantum numbers on the next slides. The first quantum number is called the principal quantum number, and that's the distance that the electron is away from the nucleus. As the number gets higher and higher, the electron is farther and farther away. So for example, 1 would be the closest distance, and then it goes all the way up to, I believe, 7 for our periodic table, and there are 7 or 8. There aren't any electrons any further away from that. And this quantum number is sometimes referred to as the energy level. So if I say that an electron is in the first energy level, that would be a principal quantum number of 1. The next quantum number is the orbital quantum number, and it describes the shape of the electron's path. So this is sometimes called a sublevel. So a sublevel is a shape. And the shapes are of 4 types: S, P, D, and F. On this page you see the S cloud, the S shape, or the S orbital. It's a sphere. The P cloud is called an ellipsoid. It kind of looks like a 3-dimensional figure 8. And later on we'll talk about the PX, the PY, and the PZ orbital. But for now, the orbital quantum number tells you the shape that the electron is traveling around the nucleus. They do not fly around in nice little circles. Sometimes it's a sphere, sometimes it's an ellipsoid, and the other 2 shapes are on the next slide. The D and F shapes are a lot more complicated. You can see from the pictures they look like crisscrossing figure 8s, or crisscrossing ellipsoids, and one kind of has a cool looking donut around the middle, kind of like a hula hoop around a figure 8. And the F shapes are even more complicated. I have some models of these in class, and I show the students. You can look at some of these pictures on page 365 in your textbook if you're interested. The third quantum number, and we have 4 of them altogether, the third quantum number, which tells the address of the electron, is called the magnetic quantum number. It tells you how many orientations there are in 3 dimensions. So the S cloud just has one orientation. It's centered perfectly about the X, Y, and Z axis, as you saw from the previous slide. But the P orbital can actually be standing up, it can be lying down, or it can be coming right out of the page in 3 dimensions. So there's the PX orbital, the PY orbital, and the PZ orbital. So there's 3 orientations, and that represents the X, Y, and Z axis, like in math class. The D orbital has 5, and the F has 7. So there's a little pattern. S has 1, type of orientation, P3, D5, F7. Now these orientations, since it's very complicated to draw, we simplify it with a line or a box. So your textbook, I believe, uses a box, and it's a little easier just to use a line. So if you were to look at the address of an electron right now, we have 4 total pieces of the address, and I've introduced 3 of them. The number 1 that you see on the page would represent the distance, and the S would represent the shape of the cloud, which is a sphere, and the single line, which tells you that there's only one way to line it up. In the next picture you see 4P with 3 boxes. The number 4 represents the distance that it is from the nucleus. The P letter tells you that it's an ellipsoid, or that 3D figure 8 shape. And the 3 boxes represent the 3 positions of this ellipsoid. It can be on the X, Y, or Z axis. So it's an ellipsoid, 3 possible orientations at a distance of 4. The last part of the address is the spin quantum number. It tells you which direction the electron is going. You can think of it as spin being up or down. A lot of people like to think of it as clockwise and counterclockwise. And the spin is represented with an arrow. So if an arrow is going up, that would mean a clockwise spin, and if the arrow is going down, it would be counterclockwise, or vice versa. Now we have the 4 parts of the address where the electron lives. We have an example here, 2s, a line, and an arrow pointing up. This represents an electron that's in a spherical orbital. It has a spin up, and it's at a distance of 2 from the nucleus, so it's a little further away than a distance of 1. Now these 4 quantum numbers tell us the location of the electron, and if you have the location, it's you can figure out where it's going to be on the periodic table, what atoms it's having a tendency to bond to, and some of the properties of that element. So if you know the address where all the electrons are, you can get a heck of a lot of information from that. Now we talk about electron configurations. We spend a bulk of the class doing practice problems, writing out the address for the electrons, and the electron configuration is just a shorthand notation that represents those 4 quantum numbers. The distance quantum number, which is called the principal quantum number, the orbital quantum number, which again is either the letter S, P, D, or F, the orientation, or the magnetic quantum number, which is either 1, 3, 5, or 7 lines, or 1, 3, 5, 7 boxes, and then the spin, and again the spin's either going to be up or down. Now there are some rules when you're filling out the address for where the electrons live, and we're going to go through those rules now. Rule number 1 is very easy to understand. An electron is going to fill an orbital that has the lowest amount of energy possible. So they start filling in an orbital called 1s, and then they fill in an orbital called 2s, and then 2p, and 3s, and so on. And you can see on the screen sort of a way to develop the pattern for where the electrons are located, and I show the students on a periodic table how this is determined as well. But for now, if you just have this list, 1s, 2s, 2p, 3s, 3p, etc., you can figure out where the electrons are going to be living. Now let's not lose focus here. The numbers 1, 2, 3, 4, 5, all the way up to 7, as you see on the screen, those are the distances that the electrons are away from the nucleus, and the letters are either S, P, D, or F. S stands for a sphere, P stands for the ellipsoid, D stands for that crisscrossing figure 8 shapes and the donuts, and F is even more complicated. So the number is the distance, and the letter tells you the shape of the cloud. So for example, down here we have 1s would fill before 2s, and 3s always fills before 3p. So the distances go up from lowest to highest energy, and the letters S, P, D, F go from lowest to highest energy. On the next page I have another picture of the energy level diagram, how the energy is increasing as you go from one shape to another. And I believe, yes, I have some electrons that fill in here. So the very first 2 electrons would go in the simplest shape, the next electrons would go in the next shape, and the next electrons, and so on. One at a time all the way until we get, I believe, to 3p is the last. Now rule number 2 basically says that you can only have 2 electrons that fit in each orientation. Now the orientation would be the boxes or the lines that I draw. So as we saw on the previous slide, as the electrons are getting added to each box, you can only put 2 in there. So for example, if you had 3 electrons, you could put the first 2 on the line called 1s, or in the orbital called 1s, and the next electron would have to go in the next shape, which is 2s. You cannot put 3 of them on a line. That is illegal. The third rule says that if you do have 2 electrons in the same orientation, they have to be spinning the opposite direction. So if you have 2 electrons, one can be spinning up and one can be spinning down, not both up, not both down. That is illegal. You cannot have a clockwise spinning electron and another clockwise spinning electron in the same shape. They would be repelling each other. So somebody's got to go clockwise, somebody's got to go counterclockwise. That's a way of thinking of spin. Rule number 4 is what I call the monopoly rule. That basically says that whenever you have more than one box or more than one orientation, you have electrons that fill in there, everybody has to get one electron before anybody gets two. So if you had 3 electrons, basically you just got to spread them out. Kind of like in Monopoly. You cannot put 2 houses on Boardwalk and no houses on, let's say, Park Place. You have to put 1 house on Boardwalk and 1 house on Park Place. So I remind the students the monopoly rule just says spread out your electrons. Rule number 5 is an exception to where the electrons are going to be placed. A half-filled orbital or a completely filled D or F sublevel, and D and F are the shapes, so the sublevel is the shape. A half-filled or completely filled sublevel actually has lower energy and it's more stable than something that's partially filled, like a partially filled D or a partially filled F. So what happens a lot of times is that an electron actually moves from one orbital to another to make this half-filled or completely filled configuration. And once it moves, it's at a lot lower energy and it's more stable. And atoms like to be at a lower, more stable configuration. So here's an example. We have 2 electrons in an orbital called 5s. Now the number 5 is the distance and the s is a sphere. And then in the next highest energy level, it's called 4d. 4 is again a distance and d is the complex crisscrossing ellipsoids. And we only have 9 electrons that are out there. And 9 is not half-filled nor completely filled. So it's slightly more unstable than if you were to have 5 or 10. So what happens in this particular element is that it borrows an electron. Watch what happens. This animation's awesome. Beep. There we go. So the electron from the 5s gets promoted to the 4d sublevel. Now the distance between, or the energy distance, if you want to describe that as like a ladder rung, the amount of energy it takes to go from 5s to 4d is rather small. So the payoff is pretty great for this element. So it takes one of its electrons from 5s, promotes it to 4d, and then the entire element is more stable. So the 4d sublevel is now full, and it's at a lower energy state than before, so it's more stable. Now the next slide, it says electron configuration practice problems. We actually write out by hand hydrogen, carbon, iodine, and bromine's addresses for all the electrons. Hydrogen has 1 electron, carbon has 6, iron I believe has 26, and bromine is like 35 electrons. We write out the entire address for them. We put the first electrons in 1s, and then they go to 2s, and then 2p, and then 3s, and so on until we run out of electrons. And again, we spread out the electrons evenly. Now I don't have any of this on the computer animation. Even the shorthand method we don't do on the PowerPoint presentation, we just do it by hand on the overhead. So you're going to have to come to class if you want to see this done. On the next page we talk about how the electrons are organized on the periodic table. These blocks actually represent the S, P, D, and F sublevels. The S column is only 2 elements thick because you can have 2 electrons in the S block. The P block is 6 elements thick because if you have the X, Y, and Z orientations and you put 2 electrons in the X and 2 electrons in the Y and 2 electrons in the Z, you would have 6 electrons altogether when it gets full. The D block is 10 elements wide because you have 5 orientations, which would be 10 electrons altogether. And at the very bottom of the periodic table is the F block. The F block is 14 elements thick because you have 7 orientations, 2 electrons in each orientation, so 7 times 2 is 14. So the reason the periodic table is sectioned off as it is because they represent the S, P, D, and F sublevels. Here's another picture of that. I copied this from one of the overheads that I had in my supplies, and you can see the S column, the P column, the D, and the Fs. Now we talk about electron configurations and their properties. So how do electrons and their addresses or their electron configurations relate to chemical and physical properties? Well, if you have the same outer shell configuration, you're going to have very similar properties. So that means if you're in a vertical group of elements, you're going to have the same a lot of similar chemical and physical properties. So for example, if you look at group 1 on the periodic table that contains the metals lithium, sodium, potassium, rubidium, and cesium, they all have one single s electron in their last orbital. For example, it's 1s, or 2s1 or 3s1, etc. And this makes them all very reactive, and they happen to react violently with water to produce hydrogen gas. And I show a video of guys throwing sodium, potassium, and rubidium and cesium in water. Well, what happens is that one single electron makes it very, very reactive. Another example of a group that has very similar chemical and physical properties is the last row on the periodic table, the noble gases. Neon, argon, krypton, xenon, and radon all have a completely filled outer shell. So does helium, but I just stick with these elements because you can see the trend. My animation seems to be off a little bit, but the electrons are in the 2s2, it's filled, the 2p6 is filled, 3s2 and 3p6 is filled, 4s2 and 4p6 is filled, and this makes them all very unreactive, or it's inert if you want the fancy term for it. So they do not produce compounds under normal laboratory conditions, because when your electron orbitals are filled, there's no place for electrons to go, so you don't have any tendency to react with anybody. And then we do some more practice problems in class. Practice problem number 1 says, which element has the last electron at 4p5? It ends up being bromine. And then I ask the students what elements would have similar properties to bromine, and that would be any element that's in its same group, which is fluorine, chlorine, iodine, and astatine. And then I ask the students what would the outer shell electron configuration look like for the element that's underneath radon. And radon is a completely filled orbital, and so the element underneath radon, if radon fills it up with 6p6, then the element underneath radon would have its last orbital being 7p6. So if you're one element below, you would have one quantum number higher. So again, radon is 6p6, so the element underneath radon would end with 7p6. Which electron is added after 6s2? You would have to look at your list of orbitals from lowest to highest energy, and it's 4f1. Which element would borrow a 5s electron to get a half-filled d sublevel? Well, we look on the periodic table and figure out which element used to be 4p4, and then it borrows an electron to become 4p5, and this happens to be the element Mo, which is molybdenum. Number 6, it says, what's the shape of the last orbital for calcium? Well, calcium's in the s block, so it would be a sphere. And how many electrons are in the last p orbital of sulfur? Sulfur is the 4th element over in the block called p. So sulfur would have 4 electrons in the p orbital. And I do a lot more examples of this in class, and I'm pointing at the periodic table as we're doing the examples. So if it's a little more complicated, just looking at the PowerPoint in my voice, I completely understand. But this is just a review. Now we completely switch gears for the last part of these notes. We talk about electromagnetic radiation. It relates to electron configurations, but we sort of have a quiz before this, and I kind of transition into this part of the PowerPoint presentation, so it's not all done on the same day. So anyway, electromagnetic radiation, what is it? Well, it's a wave of energy that travels at the speed of light. So there are many types of waves that travel at the speed of light. For example, radio waves do, ultraviolet light, visible light, things like that. And all these types of electromagnetic radiation have a different frequency and wavelength. That's basically why that's basically the fundamental difference, is the frequency and wavelength. And so I listed them from longest to shortest. So we start with the longest waves, which are radio, and they go all the way to gamma rays. I also add cosmic rays, which I believe is on the next slide. The colors of visible light, those are electromagnetic radiation waves as well. They're also listed from longest to shortest waves. So red is the longest wavelength and violet is the shortest wavelength. In terms of energy, the long waves have low energy and the short waves have high energy. Here's another picture of them. Low frequencies on the left, high frequencies on the right. Now we talk about the uses of the electromagnetic waves. Radio waves are used in communication. Microwaves broadcast TV signals, and they're also used to cook food. Infrared is what you feel is heat, and some creatures can actually detect this. Some snakes can detect the heat coming off of an animal, and so can owls. And so here's an infrared image of a cat. You can see that the color of the ears are warmer than the color of the nose, and that's because the ears are giving off more heat than the nose. And here's an infrared image of heating pipes that are under a floor. Wherever the heating pipe is, it would be a brighter spot of infrared light. So if you had a broken pipe, you could actually tell where it is by taking a picture of your house under infrared imaging as opposed to visible light. I also have a slide that shows cars that are capable of having a little camera and so you can actually see what visible light looks like, but then you can also see the infrared vision, the heat given off by objects. So when it's nice and foggy, you could still see the deer on the road. Another type of electromagnetic radiation going through the list is visible light. It's the only one that we can detect with our eyes, and it can be separated into the colors of the spectrum, and you can use a prism, which is a triangular shape piece of glass. And the colors again are listed from lowest to highest energy, and it's Roy G. Biv, red, orange, yellow, green, blue, indigo, and violet. After you get violet light, our eyes can't detect it, and that's called ultraviolet, and this is what the radiation is that gives you a sunburn. And bees can actually see this type of radiation. So when they're looking at a flower, they don't see necessarily visible light. They see the ultraviolet light. And the ultraviolet light from the sun is usually blocked by the ozone layer. Here's a flower that's taken under normal light. It's yellow, but under infrared light you can see the center is a different shade, and so an insect would know where the pollen is located, where the nectar is, because of the different center bullseye target of that flower. X-rays is the next type of radiation. Again, we're getting higher and higher energies. This is a picture of the sun taken in X-rays. Here's a picture of your arm being broken, and here's a skull. So the X-rays are higher energy, and so when they go through your body, the densities of the bone and the skin can be viewed. Then we talk about gamma rays very briefly. It's what radioactive substances sometimes give off. They're gamma rays, very high penetrating, nasty rays, give you cancer. And then the last type of radiation is sometimes grouped with gamma rays, is called cosmic rays. It's the highest amount of energy, and the gamma rays and cosmic rays and X-rays are all blocked by the ozone layer and our atmosphere. I think that's the last little blank here. It says and our blank. It's actually and our atmosphere. So that part of the animation screwed up. Now here's some goofy, interesting superhero facts. Superman has X-ray vision. The Incredible Hulk was created by an accidental overdose of gamma radiation, and the Fantastic Four were created by cosmic rays. So it's interesting that they use X-rays, gamma rays, and cosmic rays for the superheroes. Now we talk about how light's produced. Now, when an atom gets hit with energy, and you can do that by zapping it with electricity or just by heating them up in a fire, the electrons is what absorbs this energy, and those electrons absorb this energy, which is a quantum of energy, and they're capable of jumping to a higher energy level, as shown in Figure A. Now, what happens is that they immediately fall back down to what's called the ground state, is where they are supposed to be to start with. So there's an excited state, which is the higher energy level, and they fall back to the ground state, and what happens is that they spit out this energy in a particle of light or some other type of electromagnetic radiation. And this particle of light is called a photon. You might have heard this term from photon torpedoes in Star Trek. Now each photon that the element spits out is of a specific color or of a specific frequency. The frequency gives it the color. Now the color of light that's given off depends on how far the electron fell, which depends on how far the electron jumped to begin with. So if they fall a farther distance, then they give off a greater energy color. So, for instance, a small distance falling would spit out a red photon, and if they fell a further distance, it might be a blue color. So what's interesting about this is that since electrons are only located at certain energy levels or certain distances from the nucleus, they can only fall certain distances, they can only spit out certain colors of light. And what a scientist can do is they can use a device called a spectroscope, which is a prism in a tube, and it separates the colors into what's called a spectrum, or an emission spectrum, and it kind of looks like a barcode of color, which is characteristic of that element. And no two elements can give off the same spectrum of colors because no two elements have exactly the same energy levels. So for instance, if you look at the picture down below, hydrogen gives off a red colored photon, and it looks like there's a sort of a greenish color and a couple like a blue and a purple. So it looks completely different than something like helium or lithium or mercury. So each element is going to give off a characteristic spectrum of colors, and you can determine the element just by burning them. And here's another picture of hydrogen's emission spectrum. You have that red color, and then that sort of bluish color, and then like a turquoise, or I don't know how to describe it, and then there's a blue and a purple. And neon spectrum looks completely different, and so when you excite hydrogen electrons, they spit out 4 colors of visible light, and neon spits out a whole bunch of red, oranges, and yellows, and then there's a big gap, and then there's some green colors. And those are the electrons falling those certain distances. And then on this page I just show specifically how far the electrons are falling to spit out these particular colors. The visible light that hydrogen gives off when you zap it is an electron falling from a distance of 3 down to 2, or 4 down to 2, or 5 down to 2. So you have 3 to 2, 4 to 2, 5 to 2, and I guess there's another one, 6 to 2. But every time it falls down a specific distance, it gives off a certain color. So 3 to 2 is the shortest distance, so it's the least amount of energy, and then 6 to 2 would be the furthest distance, and so you get these different colors of light given off by the hydrogen because those electrons are falling. And this explains why Bohr's model of the atom is correct. It's more correct than the other ones because the energy levels are quantized. And that is this chapter, chapter 13, in a very rapid review. So we also make sparklers and do a lot of demos in class, and again those practice problems on electron configurations. So hopefully this lecture kind of helps you with class, and we'll call it a day. Bye.